Arrancamos. Pues bienvenidos al seminario. I will do it in English so that everybody can understand me. Today is our pleasure, our big pleasure, my pleasure now to introduce you Pilar Sánchez-Pastor. Pilar did her master work in the Complutense, University Complutense in Madrid. In 2014, she finished her work on elastic thickness estimations from admittance analysis. From 2015 to 2019, she had been with us as a PhD student. Her subject has been monitoring subsurface elastic properties using ambient noise. The main two case studies for his PhD have been the 2011 El Hierro eruption and the Reykjanes geothermal monitoring, the Reykjanes geothermal reservoirs. And from 2019 to 2023, 4 years, she had been as a postdoc and as an established researcher at ETH Zurich with the Swiss Seismological Service, where she had been teaching, advising students, and where she was included and has been doing research within several important research projects, mostly related to geothermal resources and natural hazards. From 2023, August, September on, she is here with us as a contracted doctor, and she is within the Stone project, basically monitoring part of a tailings dam of the Rio Tinto mine in Huelva. Pilar, please go ahead. Today she's presenting her large Nature Geoscience publication. Okay. Please.
Thank you very much, Martin, for the nice introduction. To be honest, I am very excited to be here and present my work again in this room with all of you, a lot of familiar faces. And as Martin said, I have been working in the last 4 years in the Swiss Seismological Service at ETH, and I have been involved in most of the studies and projects that were related to Iceland. And in particular, in an area that is called Hengil, that you can see there to the left. This area is very special. It's of a special interest for the geothermal companies because it's full of geothermal resources. And also from the scientific point of view, it's very interesting because there are many things going on. And in this area, we find different power plants. And there you can see one of them that is a very large power plant that we have studied in detail in this time. And then this area, Hengil, is located at around 30 kilometers away from the capital, from Reykjavik, and is as beautiful as complicated. So it's located in a triple junction between the Reykjanes Ridge, the Western Volcanic Zone, and the South Icelandic Seismic Zone. And in that satellite image, you can see that in a matter of 30 kilometers, we can see a lot of a fissure swarm that is caused by the rifting that splits the North American Eurasian tectonic plates. Also, we find several volcanic systems, and within these volcanic systems, different volcanoes. And also a few geothermal fields in the area. And as I said before, there are different power plants, but the two largest power plants in the area are these ones. The one in the north is called Nerjavelir, and the one in the southwest is called Heliseidi. And this one, Heliseidi, is one of the largest power plants in the world. So just to give you an idea, in this area, there are more than 100 deep boreholes. When I say deep, I say depth more than 1 kilometer depth. And the boreholes are targeting the reservoirs, the deep reservoirs, but also there are shallow boreholes that extract water, drinkable water from the shallow aquifers for the city, for Reykjavik. So this area is full of boreholes and a lot of activity. And this area now is also having a lot of attention because it's the next target of the Iceland Deep Drilling Project. So this project aims at finding supercritical fluids at depths of around 4 kilometers. Supercritical fluids are fluids whose temperature and pressure are beyond the critical point. And then these fluids, just to give you an idea, are very interesting in geothermal because they are expected to increase the power of the boreholes by 10 times. When I talk about power of boreholes, I talk about the fluid extraction rate. We can also talk about the temperature, enthalpy. There are different parameters, but in general, the more fluid that we can extract, the better, the more power we can generate. So all the time I will talk about power, and you can have an idea in mind that I talk about the extraction rate. So for those who are not very familiar with geothermal, here you have a representation of how an Icelandic reservoir looks like. So normally we have the reservoir that it has to have three main characteristics: that we need to have high temperatures, of course, also fluids that carry the heat to the surface, and also the rocks need to have high porosity and also presence of cracks and faults that allows fluid circulation. So in this way, we can extract hot fluids and gases from the subsurface, use them for heating, electricity generation, and then when they are cold, we reinject them back into the system. So in an ideal scenario, we have a closed system, but we will see in a few slides that is not the real case. Another thing that is quite characteristic is that we always find a cap rock that is more or less at half-kilometer depth. And this layer is very impermeable and then keeps the heat and fluids confined at depth. To talk about the extension of these reservoirs, more or less is this. So normally we find the reservoir in Iceland in this area at around 2 kilometers depth. And the horizontal extensions here, I said less than 1 kilometer, but it's very heterogeneous because at the end in this area, we have high temperatures everywhere. But the spots that are more interesting for the companies that has more profit, they vary a lot. So for instance, two boreholes that are separated by 100 meters, they present very different temperatures, pressures, and so on. So it's very heterogeneous. So we need to have very high resolution methods and techniques to try to find these spots. So just an example, despite all the methodologies that we have nowadays to image and to identify geothermal resources, in the first Icelandic drilling borehole that they tried to drill in Krafla, that is located in the north of Iceland, they heated magma. So at the beginning, the operator saw that the temperatures were lower than expected, and they continued drilling. And then at the end, at 2 kilometers depth, more or less, they heated molten rocks. And when this happens, you destroy the drill, you destroy everything, and it's an important loss of money for the company. So here we are not talking like in oil companies that the profit is very high and then they can risk more. So for geothermal companies, a loss like this has an important impact. So in this context, we had in the department, in the Swiss Seismological Service, we had different projects in order to try to decrease this risk of failure when targeting new geothermal resources. So the first project that we had was called the seismic project, and then we could deploy 40 seismic stations, broadbands around the area. Every time you see now in the presentation an inverted triangle, that means a seismic station. I always use the same. So you can see that we split it different stations, 40 stations in the area for around 3 years. And the results in this project were quite interesting. So at the end, we got funding and we could deploy 500 geophones also in this area to try to improve the results that we got. And then we split the geophones in these two areas near the power plants in the area. So the two main goals of these projects are the two main goals for me in this project. So my role in this project was basically to do two things. Imagine, to try to do seismic noise, because in Iceland, in the geothermal companies, more or less they work with electromagnetic methods, ERT, MT methods, and so on. That they work quite fine, but normally they don't employ seismic noise stuff. That is my field. So the idea was to try to deploy this array, record seismic noise, and then see what is the potential of the technique in geothermal areas. And also what was important is try to monitor the impact of geothermal energy in the subsurface. Also in this project, they were very focused on studying the seismicity, because as you can imagine here, there is a lot of seismicity, natural and induced seismicity as well. Many different clusters that here it didn't say so, but it was a quite important working package in the project. So these 2 points were my main two goals, and also in the project, but are also the main 2 points that I want to talk about in this presentation. So first, I'm going to talk a little bit about an imaging application in the area, but just a little bit, and we are going to focus more on the monitoring part. So as I said, I am going to work with seismic noise. And just a very brief introduction, seismic noise is that signal that is present everywhere and is recorded by all seismic stations. And we can observe it in upsets of large amplitude signals and can be earthquakes. The spectral content of this noise is very particular, and here I show you a typical power spectral density as a function of the period. And depending on the frequency band, we can distinguish different source mechanisms. At high frequencies or low periods, we have the thrombogenic noise, where Jordi Diaz is an expert of. Then at longer periods or lower frequencies, we have the microseisms that the Earth have. that I would like just to say here that is noise that is produced by different ocean wave interactions and ocean atmosphere, but it's this natural noise that comes from the ocean and is present everywhere. So now the question is, how can we use this seismic noise to study the subsurface? So imagine that we have two seismic stations located in X1 and X2, and we have the seismic sources in the ocean. We are not interested in studying the sources, so I am not going to talk more about that. So we have the recordings, U in X1 and U in X2. And then it can be demonstrated mathematically and with numerical simulations that the cross-correlation of these noise recordings, it gives us information of the Green's function of the medium. This Green's function is the seismic response of the medium. So it would be ideal to have it because if we have the Green's function, we know how the medium behaves if there is an earthquake, if there is an explosion, if there is whatever. And we could simulate or emulate the seismic recordings everywhere. So as you can imagine, this is very tricky to get, and normally we get approximations, but it's fine. And then there are many different types of correlations. Here I just show you the simplest one, that is just the multiplication of the recordings and applying a shift in one of the signals. So just doing that, we can study the medium. As you can see, we have two factors of the Green's function, one with positive time and the other one with negative time, because this a scenario that we have here is equivalent to this one, like the stations act as virtual sources and the waves travel from station 1 to station 2 and from station 2 to station 1. There are different assumptions that I am going to skip, but this is the idea. So that's why we can retrieve this information of the medium between X1 and X2, and we don't care about the sources. We kind of removed the effect of the sources. So here I show you a typical correlation. As I said, we have the positive time and negative. That is just that the waves travel from one station to the other one and in the other way around. And the most interesting thing is that we can observe body waves, surface waves, and coda waves in the same way as we can do with earthquakes. So this method of retrieving coherent waves by cross-correlating noise records is the so-called seismic noise interferometry. Normally, we use body waves and surface waves to do imaging, and we use coda waves to do monitoring purposes. Why? Because coda waves are formed by scattering, and then they sample the medium very densely. So if we have an anomaly, a surface wave or a body wave pass through, the ballistic waves, the direct reflected or refracted waves, pass through the anomaly and they see it, but a scattering wave spend a lot of time in the anomaly and then they are more affected. So normally, when we want to study tiny changes in the medium or time variations in the mediums, we work with the coda. And when we want to do tomographies, normally we work with the ballistic waves. So as you can see, these 2 points were my main 2 goals in the projects and are also the main 2 points that I want to talk about in the presentation. The first one is going to be the application about imaging. So I'm going to skip all the methodology. If you have any questions, you can ask me later, but I am going to go directly to the interesting part. So here you have an example of the correlation, and then we are going to focus on the Rayleigh waves. We work with the vertical components, Rayleigh waves. And then with this, we can perform a noise tomography, and then we have a velocity model of the area. And here I show you an horizontal slice of this model at 2 kilometers depth. And here we found many different anomalies that we can spend the rest of the seminar talking about them, but it's not the point. So I would like to highlight just 2. One was this one. That is not very well constrained because it's at the edge of our network, but with other techniques that we use with other stations and with active data, we saw that this anomaly is there. And it's an area that there are no boreholes. The companies don't expect to find anything there, but it's a seismic cluster going on there that is persisting all the time. But we don't have information of the area, but it can be interesting to study it more. And another particular anomaly that I would like to mention is this one that is located very close to the most powerful boreholes in the area, and maybe in Iceland. But this information is a bit sensitive, so I don't know. But they are very, very powerful, the boreholes there. And if we represent this model in another different way, so we take the ISO line of 3 kilometers per second, we can have this 3D representation. And there you can see the location of the both power plants. And these black squares and lines, white lines represent the trajectory of these powerful boreholes. And you can see they are located in the periphery of this anomaly, very close to this anomaly, and pointing towards that. So my first interpretation was we found an area that is very hot with very high temperatures. It's very exciting, but not really, because the highest temperatures here in this area are found here in the north, near this power plant. And we are talking here, we are here in this anomaly. So it's not really the temperature. Discussing with the operator, discussing with the geothermal companies, no, it's not the temperature. So what is going on here? And then at the end interpretation is that this area, it has a very high permeability. So here we have a lot of faults, cracks, and a very high density of faults that belongs to the rift, and also others that are almost perpendicular that belongs to the South Icelandic seismic zone. So this area is very permeable. So that makes that the boreholes are very powerful. That means we can extract a lot of fluids. It's very easy to extract fluids here. And also this causes a decrease in the velocity. So this is our interpretation of this anomaly. And then we thought that we found this attractive or sexy anomaly for future drilling projects. And in the publication, is a small advertisement. You can see the comparison of the model with temperature data, resistivity, gravity, and so on, but I am not going to spend more time on this. But as you can imagine, this velocity model is not constant with time. So I don't expect that the velocity is time invariant, because we are in an area with a lot of seismicity, with induced seismicity, natural seismicity. We are extracting a lot of fluids, targeting shallow aquifers, deep aquifers, changing everything. So I will expect that this velocity model changes with time. If we go back to our figure here, I would like to show you how the land behaves, how the surface behaves. And then we had measurements with INSAR, and then we estimated the vertical component of the surface deformation. That means subsidence. And here you can see the rates. So we found 3 main centers of subsidence near both of the power plants, and then in this small subfield, that is when we had the anomaly before, when these the boreholes that are very powerful are there. And then here I would like to say that this is not just happening in Iceland, and it's not only happening in Hengil. So this is very common and is observed worldwide. In most of geothermal fields, we observe a subsidence, because at the end, the fluids that we extract are not the same, it's not the same amount that the fluids that we inject. So normally, this is very common. And then in particular, I would like to show you here the mass balance in the reservoir, that it is, yes. So you can see the production fields that is with negative values, that means extraction. And then the injection fields that are represented with reddish colors, that it means injection. So you can see that the absolute values are more or less the same. We are talking about extracting or injecting 300 kilograms per second per meter square. It's a huge amount of fluids that we extract and that we inject. So that's why the seismicity, new seismicity, and so on. But as you can see, the production fields or extraction fields are much larger than the injection. So we have a deficit of fluid. In particular, in this area, we re-inject around 60% of the fluids in the system again. 40% is lost. So this causes a pressure decline in the reservoirs. And then this pressure decline is the reason why we have this land subsidence in the area. And we will see now that this pressure decline has another consequences in the system. But 1 second. And then in this context is where we said, okay, let's try to work also with seismic noise and try to estimate the velocity, the seismic velocity change with time, and see if we can see something. And then something that I didn't say is, well, that we can, well, now we are going to focus on the CODA, as I said before, because it's more sensitive to medium changes. Before we were working with the radio waves. And something that I didn't say is that we can retrieve this Green's function, the correlation, correlating 2 different stations, but also correlating 1 single station with itself. This means working with only 1 station and computing autocorrelations. That is very useful sometimes. And then in this case, again, I skip the methodology, and then I'm going to go directly to the results. And then here I would like to show you the velocity changes that we computed as a function of time of a bunch of stations that I represent here in the map. And here, with these results, we could identify many things. So we have rapid fluctuations that are caused sometimes for injection, for production, so the power plant operations that changes the medium, and sometimes you can observe that. Also, we have a seasonal variation, but what is consistent for all the stations is that all of them show a slow velocity decrease. And this velocity decrease is not the same for all the stations, it changes. So if we assume that this velocity decrease is linear, that I know is a bit tricky because in some stations we don't have a lot of data, but it's the data that we have. So assuming that this velocity drop is linear, we can estimate the rate of change of this seismic velocity. And then is just the slope. So in order to see if there is a spatial distribution of these changes, let's take the slope and represent it into the map. And then we got that. And then as you can see, there is a very high correlation actually between the land subsidence and the velocity drop. In areas when we have subsidence, the velocity drops faster, and in areas when we don't have changes in the velocity. So for instance, in some areas here and here that are far away from the power plants, we didn't have these velocity changes. We have something fluctuating around 0. And then in other areas, it correlates quite well. I would like to say that sometimes getting these insert images is complicated because when there is snow, you cannot get data. And then in Iceland, you have a lot of snow always. So in some areas, it's impossible to get resolution, and in others, yes, but this uses only data in summers because in winter it's impossible. So, but then at this point, so the interpretation was also a bit tricky, because was why the velocity is decreasing if the medium is being compacted? I will expect the opposite. So my first interpretation, I will expect the opposite. If the medium is being compacted, I will expect that the waves travel faster than slower. So what is happening here? And then in order to answer that, again, discussing with the company a lot, we got some historical borehole data. And then we know how the reservoir is behaving with time. And then let's select 3 seismic stations, these 3, that are parallel to the reef. They are located at different distances to the power plant. That means that we have a different fluid deficit in the reservoir. And then let's see what we have. And then here I show you the pressure and temperature variation during 10 years, in the reservoir for these 3 spots that we identify. And then we can see, as expected, that if we go far away from the power plant, the changes are smaller, as expected. But then what was interesting is that the pressure that is represented with the black lines, it changes in 10 years, it drops around 1.4, 1.5, the maximum megapascals. So it's a lot. And then the temperature that is represented with this, the contour plot with the bluish colors, it drops around 25 degrees. So in 10 years, the system changes a lot. And we saw that one of the consequences of the pressure decline is the subsidence. But there is another consequence that is very important, and is that we have decompression boiling. So in these systems, since the pressure is decreasing, we have a two-phase fluid. That means that we have liquid water and gas water, steam, coexisting at the same time in the pore spaces. And this makes quite tricky everything, and to estimate or to know something about the evolution of the system, because the pressure decline causes steam, but then the steam changes the temperature quite a lot, and then the evolution changes. And then depending on the amount of steam that we have, also we need to adapt the operations in the power plant, because steam can be used for electricity generation, but hot water for heating. And then depending how much steam we have, we need to target the reservoir in a different way. So here, actually, I would like to show you some measurements of the steam fraction. And then something also that was interesting for me is that most of the changes happen at around half kilometer depth in the top part of the reservoir. So the changes are not happening in the part when we are extracting the fluids, are happening there. And it's because we have this accumulation of steam, because remember that the capped rock is an impermeable layer, and then the steam that is formed is kept there, is confined there. And then we have this steam cap. And then this steam cap is the reason that we have most of the changes in the temperature, and then the changes are happening always in the top part of the reservoir. Not always, but I mean the largest changes in the top part of the reservoir. But here, so this pressure decline that is increasing with time has different consequences. For instance, you can have cold fluids that are adjacent to the reservoirs and they can come in and to the reservoir and they can cause a thermal breakdown. But also, as I said, the steam changes the thermodynamic evolution of the system, and also depending on the steam we have, if it's wet steam, dry steam, there is very different. So dry steam is more corrosive than wet steam, so this is important also for the pipelines and boreholes and so on. So there are different consequences here. I just wanted to highlight a few. But there is a good point, that is steam is a clean energy resource. So we can extract it and just generate electricity. But here in this point, I lied to you a little bit. So I said that these are measurements that we got from the companies, but it's not really measurements. It's very complicated to measure steam because for two main reasons. When we open a borehole to take measurements, the pressure difference causes that everything comes up very quickly, and then we have flushing, and then it's very difficult to measure that. So normally, we need to stop the production for approximately 2 weeks to let the reservoir reach a steady state and then take measurements. So every time we want to have a measurement, we need to stop the production for 2 weeks. So the measurements are expensive. But on the other way, also the gas phase and the liquid phase comes up with different velocities. And then to estimate how much gas I have in comparison with liquid water and different depths is very complicated. So this is not really measurements, are estimations. We know the enthalpy, and then we can estimate how much steam we have, but it's not really a measurement. It's very complicated to have a measurement, almost impossible. And something that is obvious, but I would like to remark, is that there is no boreholes, no data. So we only have data when we have boreholes. So, and nowadays there is no any technique, surface technique, that we can monitor. We can have measurements of the reservoir from the surface. We can have different techniques that we can know if there is gas formation, if there are liquids. We can use ERT, we can use different techniques, but also to reach the resolution at 2 kilometers depth is quite complicated. So it's quite expensive to do surveys in this way. With INSAR, the depth resolution is not very good, and also this depth is a bit tricky. So in this context is when we wanted to see with what we can guess with noise, but then we need to understand why we see this velocity decrease. What is what we observe? We are observing the temperature change, the pressure change, the steam change, we don't know. And then what I thought of the solution that I found was, let's perform a rock physics model and then try to see if there is a key parameter that changes the velocity. Let's see what we see with the velocity to try to monitor the reservoir. And then to perform the rock physics model, we did it in 2 steps. First, we compute the velocity for P and S waves that depends on temperature, effective pressure, and porosity. All of them are nouns. Data, we know the porosity in the reservoir, we know the pressure, we know the temperature. So easy. And then we assume that everything is filled with water. And then in a second step, we apply the Gassman equations because we know more or less, even if these measurements have large uncertainties, we use them. And then we can just replace the water that we assume with the steam that we have at each point, and then we can have the expected of the model velocity that depends on temperature, pressure, porosity, and steam fraction. And then the models that we got were these, for P waves and for S waves. So the velocity anomalies that we expect are in the top part of the reservoir, as expected, because it's when we have most of the changes. But what was interesting was that for P waves and for S waves, the model behaves very differently. S waves increase, while P waves decrease in velocity. And also the values are different. So for P waves, it seems that the change is more drastic. In order to compare better these 2 models, let's take a slice of the model at the depth when we have most of the steam, and it's here. So as we saw, if we are closest to the power plant, that means we are extracting a lot of fluids. That means we have a big fluid deficit in the reservoir. The velocity drops for P waves, while the velocity for S waves increases. And this difference comes because the density and the bulk modulus behaves in a very different way. So for this spot, the first one, the density drops 1%. We replace water by steam. Steam is lighter, less density, so the density decreases. That we understand, easy. But the bulk modulus, also the steam, is highly compressible. So to compress a rock that has steam is much easier than to compress a rock that has liquid water, oil, or another fluid. And then you can see that the bulk modulus decreases 20 times more than the density. So if we go to the equations that we go since high school, if we have a density drop, the seismic velocity for S waves increases. But for P waves, we have this density drop, but the drop for the bulk modulus is much larger, 20 times more. So that's why the velocity for P waves drops. And then I think the next slide is obvious, and is to compare the model with the observations. And then, well, first the conclusion that if there is gas formation, that's what I said, the VP, the velocity for P waves changes with the bulk modulus, and VS with the density. And then the comparison with the surface of observations is this one, at these 3 points. I represent the velocity changes with this dark red line, and then the subsidence, cumulated subsidence, with the black line. And you can see that there is a nice resemblance with the model obtained for P waves. Something that I didn't say is that we got the borehole data in a time period that we didn't have seismic stations. So we cannot compare one-to-one, and we don't know how well the observations behave or how well the model is calibrated because we don't have the data from the boreholes and the seismic recorders in the same time. So it was a pity, but it's what we had. We cannot do more. But we saw that the seismic velocity observations that we obtain are sensitive to fluid phase changes because they are sensitive to body waves velocities. And this is an interesting conclusion, but maybe a bit technical, but for those who work with noise, it's interesting because normally we assume that even the coda waves are dominated by Rayleigh waves, surface waves. If we work with the vertical component, Rayleigh waves. And then we part from that assumption to estimate the sensitivity of the waves and many other things. But here we can see that the model behaves as like the P waves. This was previously observed by other authors, that they compare the results with the receiver functions, and then they also observe a very nice resemblance between the velocities that you observe with noise and other methods with body waves velocities. So the main conclusion is that with only one seismic stations, we can estimate, or we can study, we can monitor the reservoir at depth. We don't need to stop the production. We don't need to do anything. We just need one station at the surface. And if we could, we didn't do it, but if we could discriminate between P and S waves are going to give us information about the pressure and temperature evolution, and P waves about the fluid phase changes, because we saw that P waves are more sensitive to the bulk modulus and S waves to the density. And then we can have a quite okay monitoring of the borehole of the reservoir from the surface. And then we think that this application opens new avenues to monitor reservoirs from the surface. Still, we need to work on trying to quantify or not quantify. There are many open questions yet, but the application was this one. And then with this message, well, I would like to give you a few messages to keep in mind, and is that the application that we did with seismic noise in this geothermal area were quite productive. So we saw that we could identify this low velocity anomaly that we think is quite interesting for future drilling projects. We also saw that this velocity model is not constant. With time, it changes because we have this pressure decline in the reservoir that causes subsidence. And this subsidence is a consequence, but another consequence of the pressure decline is the formation of a steam cap that changes the temperature and changes the thermodynamic a lot. And then that we can monitor the reservoir from the surface with only one seismic station. And with that, I would like to finish. Thank you very much.
Muchas gracias, Pilar. Thank you very much for this excellent and clear presentation. I'm sure there are questions, curiosities. Please do not hesitate. But you will have to speak to the micro. I will give you the micro because people online.
Sorry for my congratulations for the talk. It was amazing. Sorry for my ignorance. What do you mean? What is dry steam or wet steam?
Yeah, so at the end, yeah, because normally we talk about the two-phase fluid, and then you have droplets of liquid water and gas. So normally when you talk about dry, it's purely steam, purely gas. And then this is highly corrosive. Or yeah.
Okay, and just as a curiosity, is there an estimated lifetime for these power plants?
That is very interesting because at the beginning, when I started to work in geothermal, I said, well, it's a renewable and energy resource and so on, but well, not really. I mean, you have an impact. So as we saw, well, in the maps, you have a lot of subsidence. There is a lake very close by. There are many different problems. No, also you have some residuals of the power plant that were thrown to the lake, and then they were affecting the lake a lot, and then they had to change, and then so there are a lot of political issues involved, and also this pressure decline. What do you do? So at the beginning, I asked why you don't inject more fluids, and that's it. You inject the 60%, inject more, but then the induced seismicity is very high. So much more than production. So production, the medium behaves quite well. So it's okay. But when you inject more fluids, then you have a lot of seismicity. And always you have to have this trade-off, no? And then the expected lifetime for these power plants is maybe around 100 years or so. So depending, because this evolution changes, because also since you have this pressure drop, the efficiency of the boreholes decreases with time, because the pressure difference, no, that's why you have all the fluids and gas coming up. And then when you have this pressure drop, then the efficiency of the borehole changes. So you need to drill more boreholes in order to have the same amount of energy. So everything is complicated. So more or less 100 years. But it varies depending on the needs of the cities. And yeah.
Please. Yes. Jean goes first. Just a second.
Pilar, thank you very much for your talk. I really like it.
Thank you.
I have a question. So you did this study in the best place on earth to do
Yes.
it.
Yes.
But how is to apply all what you have been telling us in virgin areas for geothermics?
Yes. Well, it's difficult to answer. So it's true that this place is very particular, but it's also very complicated to make interpretations because there are many things going on, because you have the 3 volcanic systems and a lot of faults and a lot of complications. So, but it's true that if with virgin, what do you mean? That we don't have many studies, that we don't have information, then it's very tricky.
Have information at all.
Then it's very tricky, the interpretation, because everything can affect the seismic velocity. So we could do this interpretation because we had a lot of data. And then because at the end, if everything is changing, so with this, you can only observe the velocity change. So yeah.
Which is good what you did, because I mean, you have a lot of information that you can transport to other areas. But I think that, for example, in an area where you don't have any kind of data,
Yeah.
where you don't have
Yeah.
wells, probably it's very difficult.
Yeah, yeah. But it's always, I think, the problem with all the seismic methods in general, all the imaging methods. Only one method working alone is not working well, at least the interpretation. The results, yes, you can get the results, but interpretation, I think always is good to have as much information as possible and to gather everything for different techniques and try to interpret the results.
That shows the importance of working in pilot projects.
Yes.
You have always this data, and
Yeah.
then later on you
Collaborative, yeah.
to put more difficult sites.
Thank you. Thank you, Pilar. I love your presentation.
Thank you.
And obviously, you know, I like volcanoes. And I was wondering how the eruption that has been in the Regianes Peninsula can affect this kind of measurements and the power plants, because I have no idea.
Yes, no, actually it's a good question. But no, I don't expect that anything is changing in this point, because the eruption is a bit far away, and then it's true that there are other so in the let me go where I don't know if I have a map. Here. So in the inset map, so we are working here. That is the end of the Regianes Peninsula, and then the eruption was in the other way of the Regianes Peninsula. So a bit, I don't remember how many kilometers, but it's very far away. So I don't think this can affect in anything, but it's true that the Regianes Ridge is crossing the entire peninsula. So you have different reefs, different fissure swarms, and then in that area you have different geothermal fields. So actually, I think you have 5 geothermal fields in the entire peninsula, and this one is the latest. So that can have an effect for sure in the other geothermal fields, but in this one, I think it's far away. Yeah. I hope.
Thank you, Pilar. For a guy that doesn't that just knows that geothermal energy is a very important thing, it has been a really interesting talk. Just two curiosities. You said that you have you have the subsidence, and it's quite strong. I've seen from your graph.
Yep.
How this affects the production of the plant.
The what? Sorry?
The production of the plant. I mean, because I imagine that the subsidence is affecting a quite large region, and the plant is there. So
Yes.
how is dealing the plant with this kind of problems?
Yes. So we didn't take into account, let me go, well, here, we didn't take into account the subsidence in the model, but it's true that we could have it, but it's complicated because I expect that the subsidence changes the porosity of the medium. And the values, these velocities values that we obtain depends a lot of the porosity. So depends on the pore geometry, on the pore amount that we have in the rocks, the behavior of the seismic wave changes. So in terms of production, maybe it has an effect because at the end the pores are less, but I don't think they notice that. So I think it's maybe we can neglect that effect in terms of production. So in terms of seismicity, it's true that, but it's very complicated to take it into account. So at the beginning, I thought, let's try to also to add in the model a porosity change with time, but how much it is, we have no idea. Because at the end, we have rocks, when they drill the boreholes, they take the samples and then they go to the lab, they take measurements, but how that changes with time, we have no idea. And then, yeah.
And the second question is, this area is a very highly dynamic geodynamic system.
Yeah.
How this geodynamic display because the geodynamics is moving very fast. How this affects the
So here we have the both at the tectonic plates. So you have the North America tectonic plates, and here the Eurasian, they are spreading apart at a rate of 1 centimeter per year or so. And at this spot, in other areas of the peninsula, at different speed, but in this area, 1 centimeter. And so there are periods of extension of subsidence and periods when it's more calm. So this also affects the subsidence. But it's true that in the subsidence, if it's due to the rift, we will expect to have a geometry more like this, that you can see that there is somehow something there, but at the end is more dominating the subsidence caused by the power plants than from the rift. So you have an effect, but I do not think, again, we can neglect it.
and in the fluid transport is not affecting the fluid transport in the so highly.
Not really. What is more important are the faults that are there. So there are many big faults. For instance, the last eruption was 2,000 years ago, and then it's a very big fault that was here, and then the other one was 6,000 years ago that is located here, and these big faults are the ones that dominate the fluid transport. And then they act as barriers, and then they know where to drill to make the fluids travel to the hot areas and then straighten in other areas. So they control. So I think the already existing faults are the mechanisms that control the fluid circulation.
Okay, thank you very much.
Our plant, Pilar, has been working in a PhD at the Reykjanes Peninsula. If you remember, the first 10 years, they didn't have any injection.
Yeah.
So they were forced by Iceland, they were forced to do injection holes to compensate the large subsidence, which was the order of 20 centimeters.
Yeah, because actually, yes. So this idea of re-injecting the fluids is a bit new. So here, I think they started in 2006, and before they were not re-injecting anything. They had a disposal area when they have all the fluids that they didn't want, and that's it. And then due to the subsidence, they decided to re-inject. But this is an idea quite new.
Awesome presentation, Pilar. Thank you.
Thank you.
Have they performed any modeling of the underground flow of these injections? And because I'm surprised that they seem to be injecting, it's just one injection, one extraction, and this is not like the optimal way to inject to foster the flow.
So here they have a leapfrog model, and then the TAF model, hydromechanical models, and they have a lot of models to know the circulation of the fluids. And yes, it seems not very efficient, but yes, they work with the geometry of the faults, and then they know very well where the fluids go, and they take advantage of that. Yeah.
So they use holds to ease.
Yes, to carry
ease
the fluids. Yes, yes.
And what is the cap rock?
What is the what?
What is the cap rock made of?
The cap rock is ethmectites and zeolites mostly. So I think just so you have this mineral alteration, so you have clays, and then the mineral alteration are esmectites and zeolites. And then in the reservoir, I think you have epidotes and chlorites, and then this change is around 230 degrees, and then is when normally in the resistivity
It's
measure.
very porous. What is the porosity of the
In the reservoir,
reservoir?
well, this is tricky because you see many different values, but at the end they use a 10% of porosity for the reservoir. But in the clay cap, 10% in the reservoir. But in the clay cap, it's much smaller. It's very impermeable, I think. I am not sure.
Okay, we have now a question from the chat. First a comment, brilliant talk and beautiful presented, by the way. Okay, the question. I wonder if you could give us your view about the use of this method in other uses of the subsurface. I'm thinking seasonal or permanent storage of fluids that perhaps don't perturb so much the medium as geothermal operations do.
I didn't get it completely. So
Would you like to
hazards,
read it?
hazards, and in other uses of the surface, seasonal or permanent storage of fluids.
So in other sites,
Yes,
other
so
problems and
yes, so the easiest scenario is when you have at the end this two-phase fluid. So when you have replacement, when you have gas formation, because as we saw, when we have gas formation, then the bulk modulus drops, and then it's easy, relatively easy to measure that because you have a very important drop. So if you have a storage, for instance, of gas, I think you can monitor that quite well. That I think, yeah. So in terms of yes, other hazards, yes, actually this method is used to monitor many different hazards. So it's very easy to apply because you just need one station and deploy there and record noise. So it's very easy to deploy the method and to do the application. Again, the interpretation is what I said before, no, is complicated. So you don't have data, then it's more complicated to know the interpretation because everything can change the velocity and many factors. But yeah, but the application is very easy and you can extrapolate it to volcanic areas that I think also the steam accumulation is quite important. You can apply to other reservoirs when you have gas storage or many other different things.
yeah, exactly. I just read a comment and then we go to the next question here in the audience. You're not going too far with it if you claim that geothermal is not renewable.
Yes, it's
Just
true.
reading what is said.
Yes, it's true. It's true, and it's true that you need to be very careful when you say that. So at the end, there is actually that is very controversial in the geothermal community. And then the point is, how do you define renewable? So at the end, how is the consensus, I think, is that the future generations are not affected by the things that we do now, and then you can extract or harness geothermal energy for many years, and that doesn't compromise future generations. So that is more or less the definition, but it's controversial because if we talk renewable, the Earth's heat, you have heat a lot. No, I think we are not going to spend all of that. But we see that we have an effect. So you cannot produce geothermal energy for all the years that you want. It's not possible because you have subsidence, you have the pressure decline, you are affecting the lakes, you have also some chemicals that you throw away. For instance, I don't know if you have traveled to Iceland, that you have the Blue Lagoon, that is a very touristic place. The Blue Lagoon is just a disposal lake of a power plant that is close by. So you can make profit of it, yes, but it's an accumulation of water that is with a lot of minerals, with a lot of chemicals. So is renewable? Yes, for 100 years. Is renewable in terms of, I don't say any time, I don't think so. So always that you say geothermal energy is renewable, it has to be linked for the lifespan of the power plant because it's designed for a lifespan, not for always.
Yes, well, I add to the general comments about general congratulations on this presentation. I think it was very didactical, very clear.
Thank you.
I just two let's say, general questions. You said at the beginning that in geothermal, they rely a lot on electromagnetic methods,
Yep.
most than
Yep.
that in seismics. So after this work, can we say that the seismics supplies different information or incremental information? Or, I mean, how positive can we be about the use of seismic in these settings?
Thank you for that question, because I have a slide.
I don't know the answer. In fact, I'm not sure about the answer.
So for the tomography, actually, we perform a comparison. The figure is a bit ugly, but it's useful, and is here. So here I show you the comparison of the resistivity model that they have in the area and the velocity that we estimated at two different depths, at 0.8 kilometers and at 1.2 kilometers. And we saw that there is a very high resemblance. So when you have high resistivity, you have high velocities, and on the other way around. So that the resemblance is very good. But it's true that if you are a bit picky and you go into detail, there are some areas that it doesn't fit. And it's because you have a thermal evolution, the temperature is changing. So at the end, the resistivity methods, they rely on the resistivity that they measure that is due to the minerals that are present there. So for instance, the esmectites are formed around 230 degrees or so. So you know, if you have esmectites, you expect that the temperature is 230 degrees, more or less, to give an example. But this temperature could be yesterday, 10 years ago, 100 years ago, or 1,000 years ago. So you don't know, because once the minerals are there, they are not going to disappear. So sometimes that happened, for instance, in Kravla in the north, that they expected very high velocities, and then when they drilled, they didn't see these velocities, not temperatures, and then when they drilled, they didn't see these temperatures, because you have the thermal evolution. So I think comparing seismics with resistivity, you can get information of the thermal evolution. And we compare in some areas, but we didn't have enough resolution, so I don't show the results. But in some areas, when we have this discrepancy between the seismics and the resistivity, the company told me that the temperature is changing a lot in these areas. So in sometimes the system is heating up, and sometimes the system is cooling down. And then this difference is when you can retrieve combining both methods. So seismic is better, I don't dare to say that. But the combination of both things, or how, so I think applying seismic noise stuff is useful in these areas.
And just it's more a question. I understand that you don't have work with induced seismicity, or let's say induced in seismicity in the area, but I don't know if there are in the same research project there are people doing work with this.
Yes, a lot. Actually, here, and we published a paper about the seismicity. So here you have, this is the same area, and then we could identify different clusters. So here the power plants are, this one is the one in the north, and the other one is here, the stars. And then we have different seismic clusters that are always there. So for instance, this seismicity that is here is natural, is quite deep, but the induced seismicity normally is at 2 kilometers depth. That is at the depth of the boreholes, basically. And then here you have a comparison also of the seismic clusters. And normally they have magnitudes up to 2 point something.
Thank you, Pilar, for your presentation and amazing work. I hope it's not the first discovery, big discovery. I hope more discoveries come for you. And my question is in the line of induced seismicity, but I think I was thinking on that and I answered myself. But if the induced seismicity was high, could you work with the CODA doing interferometry?
So here, I mean, ideally, yes. So here, it's true that we have a good catalog, a very good catalog when we could deploy these 500 stations. So I worked with the broadbands, that was 40 stations, and then with the 500 stations, we got a very nice catalog, but are 500 stations. So to build the catalog took a lot of time using machine learning techniques and many different stuff. And then we have a very good catalog that I think we are planning to work with that and to do something, because we have a lot of seismicity and yeah. And it's true that we also did a seismic tomography with the earthquakes that we had with the other array. The resolution was not very high because the array was very spread, but worked quite okay. So also they could identify some anomalies that were interesting. And working in the CODA, we didn't apply anything. I think, yes, ideally you can do it, but we didn't apply.
But maybe the earthquakes are
With the earthquake.
small and they don't have a lot of.
Yes, that is the problem. You have a lot of micro seismicity and sometimes big seismicity. So you can reach a magnitude of 2, and then with that you can use it. But you don't have that many all around the area to use.
So new results from this project are expected. No?
Yes, I think so.
Okay,
Yes.
and
We
to
have a lot
compare
of
with your
data. Yes.
Okay.
And if you
Let's
have any
see.
idea, let me know. Now the data is going to be open access soon. So
To finish, a last question. Okay, so it's my turn. I don't see a hand raised. Pilar, do you think with the station deployment you showed us, it would be possible to do 4D tomography? Yes.
sorry, was a very honest answer.
It was clear. I know I'm aware of problems, but I
don't
just
think-
contacted for 4D tomography, and we are again, I guess, slipping into that. And
It will be interesting, but I think the
you think
parameterization,
it's feasible with that deployment of station and the data you have seen and what you have done? Do you think it is sufficient robust to map, to image already with tomography, or what would be missing? Any comment?
I don't know, because the maximum changes that we observe are around 2%. And then I think when you do the tomography, these regularization parameters that you have intrinsic, I don't know, you can resolve an anomaly of 2%. In the best scenario, 2%. In other areas, it's smaller. So at least with the methods that I use, the codes that I used, I don't think I can cope an uncertainty or to reach an uncertainty, to resolve an anomaly that is 1% or so, and to do a 4D tomography. I don't think so.
Methodologically, the robustness needs to be.
At least the methods that I used, I wouldn't do it.
Okay.
But maybe there are other techniques with much better resolution that you can have a resolution of 1%, and then it will be.
Okay, thanks again for everything. Thanks to all of you.